Alright, this video is going to be a walkthrough of Exam 2 for MA 266 from spring 2024. So let's jump into it. Alright, number 1. If the method of undetermined coefficients is to be used on y double prime minus 2y prime plus 5y is equal to x sine of 2x, which of the following is the correct form for a particular solution y sub p? So in this question, we're dealing with a inhomogeneous linear second order differential equation. It's inhomogeneous because of this x sine of 2x term here, and it's second order because there's a second derivative here. That's the highest derivative of this differential equation. So in order to find a general solution for this kind of equation, if this are homogeneous, then we just have to come up with a complementary solution and call it a day. But we also have to come up with a particular solution like the question mentions over here. And so the general solution to a differential equation like this would end up looking like y of x is equal to y sub c of x plus y sub p of x, where y sub c, this is the complementary solution, and then this y sub p term is the particular solution. And finding the complementary solution is the same process as if this was a homogeneous differential equation. So to do that, you'd set up a characteristic equation where you'd say that, I guess like x of r is equal to r squared minus 2r plus 5. And what this characteristic equation is it's just rewriting the original homogeneous part, of the original differential equation in algebraic terms and replacing each derivative with an exponent. So a second derivative becomes a 2, a first derivative becomes a 1, and then this y is not a derivative, so just treat it like I guess just a constant. And then we set it equal to 0 and solve for r. And the three ways you could do that is factoring, completing the square, or if you're extra paranoid, you can use the quadratic formula. But for this question, I'm going to complete the square because I can't really factor this nicely. And also, I'm pretty sure we're going to end up with a complex r value, just looking at this. So when we do that, we'll say that to complete the square, you'd have, r squared minus 2r plus 1 plus 4 is equal to 0. So r minus 1 squared is equal to negative 4. So r minus 1 is equal to plus or minus 2i. So r ends up being equal to 1 plus or minus 2i. So as expected, we ended up with a complex term for r. And so we won't be able to just come up with a complementary solution right off the bat because of that. We're going to also have to make use of Euler's equation, which goes like this, where if we had a term where we said that we had e to the 1 plus or minus 2i x, we can rewrite this as just saying we have a constant here, so c1 e to the x, because we have a 1 here. What this is actually, yeah, let me rephrase. So we know that a complex number has a real and an imaginary part, so a plus or minus bi. So in this case, a would be 1 and b would be 2. What you do is you split this up where you keep the real portion with the e term, and then you include the b term with some trigonometric functions. So what your new term would end up looking like is you'd have some constant, so c1 e to the ax times cosine of bx plus c sub 2 e to the ax again times sine of bx. And what this allows us to do is it allows us to come up with two terms from a single complex number. And so in this case, since a is 1 and b is 2, our complementary solution for this differential equation is going to end up being that y sub c of x is going to be equal to c1 e to the x times cosine of 2x plus c sub 2 times e to the x of sine 2x, like this. And so now that we have our complementary solution, we can come up with a particular solution from here. And we can use this information to come up with a particular solution. And so Now what I'm going to do for the particular solution is I'm going to completely focus on this x sine of 2x term here, because that's what we care about now. Um, and so to do that, we're gonna use the method of undetermined coefficients, like the question says, and that just consists of coming up with a series of guesses for a term, or no, I should say educated guesses, because they're based on something. And so what you'll see here is in this term we have a sine of 2x term and an x here. So for our guess, let's say like if this were to come from a characteristic equation, we could deduce that the r value that gave us this was equal to just plus or minus 2i, because there's also no e term here, so that means that the real part was 0 and that there's only a complex term. So we have a plus or minus 2i, and then also there's x in front tells us that this was a repeating term. This was a duplicate, meaning that if this came from a characteristic equation for a complementary solution, that we'd end up with 4 total terms, or I guess 2 sets of sine and cosine terms. So our initial guess, the guess that we can come up with for this as a result would be x sub p, no, not x, y sub p of x. Yeah, y, no, that's supposed to be a y. Y sub p of x is going to be equal to ax cosine of 2x plus bx sine of 2x plus c cosine of 2x plus d sine of 2x. And so this takes care of all of the conditions given to us from this inhomogeneous portion here, because we've taken care of the fact that this could be a duplicate because of the x, and we also matched up with this 2x term here. And so the last thing we have to do is we have to make sure that our particular solution does not have any terms conflicting with our complementary solution. And the way to tell that is just by looking at the complementary solution and seeing if it matches up with our particular solution, which it doesn't, because it looks similar, but they're not actually identical. You'll notice that our complementary solution has an e term here and an e term here, whereas our particular solution doesn't. So we don't have to take any additional steps to make the particular solution different from the complementary solution. Even though this does have a cosine 2x and a sine 2x term, there's no e term, so it's not exactly the same. And so we can just tack this on to the end of the complementary solution and come up with a complete general solution for this differential equation, or at least the form of that general solution. And the reason why you'd have to change it up a little bit if it did conflict with the complementary solution is because if you just left it as is and you were to complete this to find the general solution and evaluate for a and b, when you plug this particular solution back into the original differential equation here, you're going to find that it's going to simplify down to 0 is equal to x sine of 2x. And that's wrong. That's incorrect. And so that's a good way to check if you have the right guess from the method of undetermined coefficients. And so we don't have to do that. So we pretty much have an answer here, which is this particular solution over here. And let me clean this up a little bit. Let me rewrite it in terms of the way the answer choices are. And the answer choices have grouped the sine terms and the cosine terms together. I'm looking, and so as a result, I think the answer for this is going to be D. So if we rewrite our initial particular solution here, I'm going to rewrite it by grouping the sine and cosine terms. So we end up with ax plus c times cosine of 2x plus bx plus d sine of 2x. And now I know the answer has it as ax plus b and cx plus d. Yeah, it has it as ax plus b and cx plus d instead of what I have here, but that's okay. It's still the same general form. You can kind of see how it matches up. So yeah, so the answer to this question is going to be D. Number 2, transform the given differential equation x double prime plus 2x prime minus 2x equals cosine 4 of t into an equivalent system of first-order differential equations. So yeah, it's asking us to set up a system of differential equations, and there's some pretty important information in this line down here of how it wants us to set up the differential equation, or the system of differential equations. So the first thing I notice is that it's asking for a system of first order differential equations. So that means that the highest power, no, not the power, the highest derivative in each of the equations that we come up with has to be only to the first derivative. So for example, like in this original differential equation, this is a second order differential equation because the highest derivative is a second derivative. So our new equations, the highest derivative has to be a first derivative. And so what we're going to do is we have to come up with new variables to relate these x terms into something, these x terms into something else. So I'm gonna keep this first order highlighted because that's very important for this entire question. What I'm gonna do is I'm going to come up with two variables because, well, it's the question, the options kind of conveniently kind of let us know what like the names of the variables we should be using. So I'm going to be using x sub 1 and x sub 2. And the reason for that is because we want things to be no more than a first derivative. And in that case, all we need is two variables. So we need to set, yeah, so we have our x sub 1 and our x sub 2, and we need to find something for x sub 1 prime and x sub 2 prime, and nothing more. So no x sub 1 double prime or x sub 2 double prime because it's asking for a first order differential equation. So the first thing I'm going to do is I'm going to start with the original variable x without any derivatives and just say that x sub 1 is equal to x. And then I'm going to work my way up from there through these derivatives to relate it all to what we want here. So from here, to find x sub 1 prime, we can just differentiate x sub 1. So we can just say that x, that's not a pen. We can just say that x sub 1 prime is equal to x prime. And then we can do another thing and relate this to x sub 2. So I'm going to do just that and say that x sub 2 is equal to this. We can say that x sub 2 is equal to x prime, which is equal to x sub 1 prime. And what this does is this allows our new variables, it lowers the highest derivative by 1. And you'll see why when I finish coming up with things for these terms. Because from here, the next thing we can do is we can come up with something for x sub 2 prime and say that x sub 2 prime is equal to x double prime, which is equal to x sub 1 double prime. But we don't need this x sub 1 double prime because we want our highest derivatives for x sub 1 and x sub 2 to just be the first derivative. So for this question, I'm just going to say that x sub 2 prime is equal to x double prime, since x sub 2 is equal to x prime. So at this point, we've done most of what we need to do from here, because we have terms for x sub 1 prime, x sub 2, and x sub 2 prime only going up to the first derivative. Yes, this is a second derivative, but this is what matters here. The x sub 2 term, that's only a first derivative. So at this point, we can plug in the things that we came up with into the original differential equation and then separate it into two different equations. So I'm going to do just that. So this new equation ends up becoming x sub 2 prime plus 2, where is it? X sub 2 minus 2 x sub 1 is equal to cosine of 4t. And the reason why I use these terms specifically is because, like I mentioned earlier, we want this entire thing to be no higher than a first derivative because it's asking for a system of first order differential equations. So you'll see that every single term in here, the highest derivative is a first derivative. The other thing is we want to completely eliminate these x terms and only have this equation in terms of x sub 1 and x sub 2. So that checks off the two things we need. no higher than a first derivative, and only x sub 1 and x sub 2 terms. And so from here, we can separate this into two equations to come up with a system of differential equations. So the first thing we can say is um, x sub 1 prime is equal to x sub 2 because we said that here. So that's already one of the equations. X sub 1 prime is equal to x sub 2. And then we can find something for x sub 2 prime. And for that, it's just as simple as moving things around in this equation to one side so that you have x sub 2 prime isolated. So that's just as simple as moving these terms to the other side. So we can say that x sub 2 prime is equal to cosine of 4t plus 2x sub 1 minus 2x sub 2. And so this is our new system of differential equations. Or we're done here. We can pick an answer. You'll see that it's a first order system of differential equations because the highest derivative is the first derivative. So for this, the answer ends up being E. I believe it. Yeah, it ends up being E. And another thing also, since originally we said that x sub 1 prime is equal to x sub 2, that automatically eliminates a and b, because a and b says that x sub 1 prime is equal to 2x sub 2. Yeah. And then we can also get rid of c as well, because it says that x sub 2 prime is only equal to cosine of 4t and doesn't account for these terms here. So yeah, so the answer to this ends up being E. Number 3. A damped mass spring system is set in motion and undergoes an external force of the form f of t is equal to cosine of omega t. Which of the following plots represents the qualitative behavior of the displacement x of t of the mass after a long time has passed? So it's in the question. We're dealing with a damped mass spring system. So as a result, we can model a differential equation that looks like the general form for a damped force oscillation. And so the differential equation for a question like this would look something like mx double prime plus cx prime plus kx is equal to f sub 0 of cosine of omega t, like this. And this right side of the equation here would be the external force, so f of t, which is given to us in this question. So we can come up with a more specific differential equation for this question where we say that mx double prime plus cx prime plus kx is equal to just cosine of omega t. So yeah, let me clean up this k here. And so let me also get rid of this here to avoid any confusion. And so to find a general solution for a differential equation like this is an inhomogeneous linear differential equation. So we're going to have a complementary solution and a particular solution. So the general solution for a differential equation like this would look like x of t is equal to x sub c of t plus x sub p of t. And so for this kind of question, since we're dealing with a more generalized differential equation, I'm mostly going to be focusing on the particular solution here because that's what's going to matter more for this question. And we can find that particular solution by using method of undetermined coefficients for this kind of differential equation. And if you were to do that, the particular solution would look something like x sub p of t is equal to a cosine of omega t plus b sine of omega t. And the question is asking what is the qualitative behavior of the displacement of x of t after a long time has passed? And so we can treat that as it's asking like, how does the general solution of this differential equation behave as t approaches infinity? So to start, we can say that when t is equal to 0, we can say that the general solution behaves like this, where it includes the complementary solution and the particular solution. So when t is equal to 0, then the general solution will behave where x of t is equal to x sub c of t plus x sub p of t. And the reason for this is because the difference between the complementary solution and the particular solution here is that the complementary solution is dependent on initial conditions, whereas the particular solution is not. And the reason we know this is because usually the complementary solution, it might look something like, I don't know, you could say like x of c of t is equal to like some constant e to the whatever x plus c2 times e to the 3x or whatever, so on and so forth. And to find C1 and C2, you'd have to take into account the initial conditions. Whereas for the particular solution, this A and this B, to find them, it's not dependent on what the initial conditions are, which means that the particular solution is a steady periodic solution. And steady periodic solutions are independent of initial conditions. And it's also in the name. Steady periodic solutions are steady, so they're not erratic. They don't go all over the place. They kind of stay the same with the same period steadily. And so from there, we can already eliminate 3 answer choices. We can get rid of A, we can get rid of B, and we can get rid of D. Because the only steady the only steady solutions here are C and E. And I also know that the answer is going to be C here, and I'll show you why. So as I mentioned, that when t is equal to 0, this just behaves like the general solution here. But as after a long time has passed, like the question says, when we treat that like as t approaches infinity, the solution behaves a lot more like just only including the particular solution. The behavior of the complementary portion becomes pretty insignificant after a long time has passed, because the initial conditions matter less and less as time progresses. And so if you were to graph this, so let's just say, let me set up 2 graphs. So you have a graph when t is equal to 0. The graph is going to look it's going to kind of be all over the place, because it includes information from the particular solution and the complementary solution. So you'd have some crazy wave that, I don't know, it starts up here, is all over the place and stuff, like this or whatever. And then as t approaches infinity, I'll put that down here. As t approaches infinity, it gets the complementary solution becomes more and more insignificant, like I mentioned, because the initial conditions matter less and less, and the information from the particular solution matters more and more. And since we know that the particular solution is a steady periodic solution, the graph is slowly going to even out and just become a steady wave like this, with a steady period and steady behavior. And we know that the particular solution is this a cosine omega t, b sine omega t thing. And if you were to graph that, generally speaking, that looks a little something like this. And so as a result, we know that the answer is going to be C, because the general solution behaves like this or like this after a super duper long time has passed. And so yeah, so the answer to this question is going to be C. All right, number 4. Consider the linear system of differential equations x prime is equal to this matrix times x. So this is the cool thing is the system of differential equations has already been put into matrix form for us. So x prime equals ax, where a is this matrix. And this question is focusing on the behavior of the system, the general solution of it at the origin. And that is dependent on what the eigenvalues are for the general solution. And in order to have a saddle point, we need to have a positive and a negative real eigenvalue. Has emphasis on real, not complex. We can't have a complex eigenvalue because that would give you a spiral source or a sink, which is not a saddle point. So to get started, I'm going to approach this using the eigenvalue method first. So you take the determinant of a minus lambda I and set that equal to 0, where this negative lambda I is the identity matrix for lambda. So negative lambda, and negative lambda diagonally like this. So what that ends up looking like, the determinant, is you'd have 1 minus lambda, negative alpha 4, and negative 1 minus lambda equal to 0. And in order to take the determinant of a 2 by 2 matrix, you'd have to multiply the top left term times the bottom right term and subtract the bottom left term times the top right term. And so what that ends up looking like is you have negative 1 minus lambda times 1 minus lambda minus 4 times negative alpha equal to 0. And so let me solve this out. So you end up with negative 1 plus lambda minus lambda plus lambda squared plus 4 alpha equals 0, which reduces further down to lambda squared minus 1 plus 4 alpha. And I'm going to rearrange these terms here, and that's going to make sense in a few moments, because here we have a quadratic equation, and in order to determine the alpha that we need to satisfy the conditions of this question, we're going to have to use a quadratic formula. So I'm going to rewrite this. Equation up here as a lambda squared plus 4 alpha minus 1. And then group this together, and then this is going to become our C term, and this is going to become our A term. And then we don't have a B term, so B is just going to be 0. And recall that the quadratic formula is negative b plus minus the square root of b squared minus 4ac over 2a. So then when we plug everything in, you end up with 0 plus or minus 0 again minus 4 times 1 times 4 alpha minus 1 over square roots over 2. And for this, since we need a positive and a negative real eigenvalue, I'm just going to focus on this radical over here, because that's the only thing that matters for this. And so when we clean up everything, we end up with plus or minus the square root of 4 minus 16 alpha. And the reason I'm keeping this plus or minus here, it's so just to clear things up for me, so I know, yeah, since we need a positive and negative real eigenvalue, and since b is 0, that's guaranteed to happen, assuming that this square root becomes real. And so since we need a real number from this square root, we need 16 times alpha to be less than 4. So if we set up that inequality, you end up with 16 alpha is less than 4. And when we solve this inequality, we'll find that alpha has to be less than 1/4. And so in order to have a positive or negative real eigenvalue, alpha has to be less than 1/4, not less than or equal to, because if it's equal to, then you end up with 0, which does not satisfy the conditions that we want here. And so as a result, in order to get a saddle point, alpha has to be less than 1/4, meaning that the answer is going to be B. All right, let x of t be equal to this vector, be the particular solution to the initial value problem of this system of differential equations, or x prime of t is equal to this matrix times x of t, and then x of 0 is going to be equal to this value, this vector. So we have a system of differential equations that's already been put into matrix form for us, as well as an initial value problem. So we're going to have to find a general solution and then solve the initial value problem with that to find their particular solution, and then ultimately find this value here of x sub 1 of 1. So to do that, since we have a system of differential equations here, we can find the general solution by using the eigenvalue method. And to start, we'd have to find the eigenvalues of this matrix first. So to do that, you'd find the determinant of a. Wait, that's not an a, that's a 1. Give me a second. The determinant of a minus lambda I, and set that equal to 0, where a is this matrix and negative lambda I is the identity matrix of negative lambda, which looks a little something like this thing. So When you plug everything in, you end up with the determinant of 1 minus lambda 2 to 1 minus lambda, set that equal to 0. Uh, and so when you do that, to find the determinant of a 2 by 2 matrix, you multiply the top left by the bottom right, and then subtract the bottom left times the top right, so you end up with 1 minus lambda times 1 minus lambda minus 4 is equal to 0. And when you simplify that down, you end up with lambda squared minus 2 lambda minus 3. And from here, to find lambda, we can just factor this. You can either factor or complete the square, or if you're feeling really paranoid, you can go as far as using the quadratic formula, but I think for this one you can just factor it, because when you factor this, you end up with lambda plus 1 times lambda minus 3. Yeah, and so as a result, your lambda ends up being equal to negative 1 and 3. So we have our eigenvalues. And so the cool thing about that is that eliminates a bunch of answer choices from here right off the bat, because they don't match the eigenvalues that we have. So that we can get rid of B, we can get rid of D, and we can get rid of E. So all that's left is just A and C. And so from here, now we have to find our eigenvectors. So to do that, we're going to plug in our eigenvalues back into this matrix over here, and set up an equation that looks something like this. So I'll start with the first eigenvalue, so negative 1. So when lambda is equal to negative 1, the matrix ends up looking like this, where you have 2, 2, 2, and 2. And then you're going to multiply this by x sub 1 and x sub 2 and set that equal to 0 and 0. And then when you multiply these, when you do some matrix multiplication, you end up with an equation that looks like 2x sub 1 plus 2x sub 2 is equal to 0. And from here, we just have to pick two numbers for x sub 1 and x sub 2 that satisfy this equation that aren't 0 and 0, and we'll have our eigenvector. So I'm going to rearrange things a little bit, so we end up with, when you simplify things down, you end up with x sub 1 is equal to negative x sub 2. And so I'm just going to pick 1 and negative 1, because those are simple numbers. So the corresponding eigenvector for this eigenvalue is 1 and negative 1. Yeah, like this. And then we rinse and repeat the same process for the second eigenvalue, so 3. So when lambda is equal to 3, you end up with a matrix that looks like negative 2, 2, 2, and negative 2. Rinse and repeat the same process, x sub 1, x sub 2 is equal to 0, 0. And one of the equations we can come up with is, I'm going to use the top row. I'm using the top row for both of these, by the way. It doesn't really matter, but I'm using the top row. So you end up with negative 2 x sub 1 plus 2 x sub 2 is equal to 0. Pick two numbers. When you move things around, you end up with x sub 1 equals x sub 2. So I'm going to just use 1 and 1 as a result. So the corresponding eigenvector for this eigenvalue is going to be 1 and 1. And so from here, we can write up our general solution, which is going to look like this, where we can say that x of t is equal to c sub 1 times our first eigenvalue, which is negative 1, times t, so negative t with its corresponding eigenvector of 1 and negative 1, plus c sub 2 of e to the 3t, which was our second eigenvalue, plus its times its corresponding eigenvector of 1 and 1. And from here, we can use our general solution to solve the initial value problem right here. So we know that when t is equal to 0, the general solution is equal to negative 1 and 2. And we can use that information to find these constants. So I'm going to put it into an equation like this, where we can say that negative 1, 2 is equal to c sub 1 times 1, negative 1, plus c sub 2, 1, and 1. And I got rid of these e's because I set it equal to 0, so e to the 0 is just 1, so that gets rid of those. And to find c1 and c2, there are a variety of different ways you can do it. You can set up a couple of equations and find them that way. Or if you're comfortable with linear algebra, you can set up an augmented matrix and row reduce it to find c1 and c2. And I like these numbers. They're pretty simple, so I'm going to set up an augmented matrix and put it in the form of this. So you have 1, 1, negative 1, 1, bar, negative 1, 2. And I'm going to row reduce this because these are some pretty simple numbers. So when you row reduce it, you end up with 1, 1, negative 1. And I'm going to get rid of this number, so you end up with 0. And then and you end up with 2 here. And you end up with 1 here. And then we do that again. And then, so then this becomes 1, 0, 1, 1 half. Then when we move these back up, you end up with 0, and this becomes 3 halves? Wait, no, actually, no, this becomes negative 3 halves. My bad. Yeah. And then, yeah, that's not a z, that's a 2. These are both 2's, not z's. So after doing the row reduction, we found what C1 and C2 are. So we can say that C1 is equal to negative 3 halves, and C2 is equal to 1 half, like so. And so we've solved the initial value problem. So the particular solution to this initial value problem is going to end up being that x sub p of t, or no, I'll just say x of t. Actually, wait, let me write this down here. So we can say that x of t is equal to negative 3 halves times e to the negative t times 1 and negative 1 plus 1 half times e to the 3t times 1 and 1. And the question is asking us for x sub 1 of 1. And x sub 1 refers to all of the numbers in the top portion of these eigenvectors. So I'm going to be focused on this 1 and this 1. So when we plug in 1 for t, we end up where x sub 1 of 1 is equal to negative 3 halves e to the negative 1 plus 1 half e to the 3. So our answer to this question should be A. Oh, and it matches up perfectly. We don't have to move anything around beforehand, so that's nice. So yeah, so the answer to this question is going to be A. Oh yeah, and then also here's the here's the entire problem from the beginning to the end of how we got here. All right, number 6. Solve the initial value problem of x prime is equal to some matrix times x, and x of 0 is equal to 1 and 9. So we're dealing with another system of differential equations here with a initial value problem. And right off the bat, I know that, so since this is a system, we're going to have to use the eigenvalue method to come up with a general solution. And I know right off the bat that we're going to end up with complex eigenvalues, because if you look at the answers here, you're going to see that there's a sine and a cosine term in the vector of each of these answers, which means that is it's a complex. It makes use of a complex eigenvalue that was converted into something something with trigonometric functions by using Euler's identity. And so from looking at these answer choices, we can deduce that the eigenvalue that was used here is going to be lambda is equal to negative 1 plus or minus 3i. And now if you're still not convinced just by looking at this, you can still find the eigenvalues by just doing the normal computation. So I'll do just that. And to do that, you would have to set up the determinant of a minus lambda I and set that equal to 0. And A is going to be equal to this matrix over here, and minus lambda I is just the identity matrix of negative lambda, like this. So when you plug everything in, you end up with a determinant that looks like this. So negative 1 minus lambda negative 1, 9, and negative 1 minus lambda. And you set that equal to 0. So when you do that, to find the determinant of a 2 by 2 matrix, you're going to multiply the top left by the bottom right and subtract the bottom left times the top right from the first product. So that would end up looking like negative 1 minus lambda times negative 1 minus lambda plus 9 is equal to 0. And when you simplify this down, you end up with lambda squared plus 2 lambda plus 10 equal to 0. And to find lambda from here, looking at this, I can't really factor it. And then, so the other two ways to find lambda would be by completing the square or by using the quadratic formula. And so for this one, I'm going to complete the square to do that. So when you complete the square, you end up with lambda squared plus 2 lambda plus 1 plus 9 is equal to 0, which ends up being equal to lambda squared plus 1 squared is equal to negative 9, which simplify. Oh wait, not oh wait, no, this is supposed to be just lambda, not lambda squared. Yeah, there we go. So then this simplifies down to lambda. That's not a good lambda. Whoa, there we go. Yeah, lambda plus 1 is equal to plus or minus 3i. So lambda ultimately is going to be equal to negative 1 plus or minus 3i, which matches our initial guess here of negative 1 plus or minus 3i. So after doing the computation, you can see that, yeah, we do in fact have a complex eigenvalue. So from here, we just have to find an eigenvector. But the cool thing is, since we're dealing with a complex eigenvalue, we only have to come up with one eigenvector because we're only going to be using one side of this eigenvalue. Because this is two eigenvalues in one because of the plus or minus thing here. And so we only need to use one of those, and we can come up with two terms from that one eigenvector, an eigenvalue. And for complex eigenvalues, I find that it's good practice to always use the plus version of it, so negative 1 plus 3i, and not the minus version of it. And the reason why is because when you eventually convert it to something else, when you come up with your two parts using Euler's identity, you're going to have to move things around. You're going to have to flip some signs around here and there. And so it adds more room for mistakes. Whereas if you just use plus, you don't have to do any of that. So even if it seems easier at first to find the initial eigenvector using the minus term, I would still recommend using the plus term. So I'm going to do just that. And to find the eigenvector, you just plug your eigenvalue back into this matrix and set up an equation that looks like this. So if we say that since lambda is going to be equal to negative 1 plus 3i, then the corresponding matrix is going to end up being negative 1 plus 1 minus 3i, so negative 3i, negative 1, 9, and negative 3i. And you're going to multiply that by x sub 1 and x sub 2, and set that equal to 0 and 0. And then you do some matrix multiplication, and you can pick either the top row here or the bottom row. For this one, I think I like the bottom row more, so I'm going to use that. So you end up with 9, oops, let's get rid of that. 9 times x sub 1 minus 3i x sub 2 is equal to 0. And then you have to pick an x sub 1 and an x sub 2 term that's not 0 and 0. That satisfies this equation. So when we move things around and simplify things a little bit, we end up with 3 times x sub 1 is equal to I times x sub 2. And you can see I use the bottom row here because now both sides are positive. I think it's easier for me when I don't have a negative term anywhere. So that's why I ended up using the bottom term. So the two numbers I'm going to pick, I'm just going to pick their opposites. So we end up with an eigenvector that looks like I and 3. Where I is going to be x sub 1 and 3 is going to be x sub 2. Yeah. And so, yeah. And so now that we have we have an eigenvalue and we have our corresponding eigenvector. So we can come up with a general solution from here. And so this is where Euler's identity comes in. Usually with a general solution, we just say from here that we can say that x of t is equal to, I don't know, some constant times e to the, for here I guess you'd say like -1 plus 3i t times its eigenvalue of I and 3. But we can't really do anything with this. So this is where Euler's identity comes in. And so we can say, so we know that we can say that e to the a plus or minus bi t, this can be rewritten by separating the real part from the complex part. So you end up with e to the a of t times cosine of bt plus I sine of bt, where a is the real part and b is the imaginary part. So if we plug in this thing into Euler's identity, we end up with a new term that looks like e to the -t times cosine of 3t plus I sine of 3t times the corresponding eigenvector of I and 3. And so the two parts that we need to generate from this, and I forgot a parenthesis there, the two parts that we have to generate are going to be a real part and an imaginary part. And so I'm going to start with the real part. And the real part can be found just by distributing a real part times a real part, or an imaginary part times an imaginary part. So I'm just going to match those two together. So for our first part of the solution, I'm going to say that x of t is equal to c sub 1 times e to the -t times the real part here. So I'm going to multiply this I sine of 3t times this I, which will give us negative sine of 3t. And it's negative because I times I gives us -1. And then I'm going to use, for the bottom portion, I'm going to use cosine of 3t and 3 here, which gives us 3 times cosine of 3t. And then we use the same process to come up with an imaginary part, except instead of trying to come up with real parts, we try to come up with imaginary parts. So we end up with c sub 2 times e to the -t. And this time, I'm going to multiply cosine with I, because that gives us an imaginary part, because cosine of 3t times I just gives us I cosine of 3t. So, and then we don't have to write the i's here, so we just end up with cosine of 3t. And then do the same thing for the bottom, so we end up with 3i of sine t without writing I. There we go. Like this. So yeah, so our general solution to this system ends up being this equation right here. So now we can solve our initial value problem, and it's also conveniently written in vector form for us. So I'm going to set up an equation to solve this initial value problem, and it says that x of 0 is equal to 1 and 9. So we can plug in 0 for t. So when we do that, we can say that 1 and 9 is equal to c sub 1 times negative sine of 0, which is 0, and 3 cosine of 0, which is 1. So we end up with, oh no, 3 cosine of 0 is 3. So 0 and 3 plus c sub 2 times cosine of 0, which is 1, and 3 sine of 0, which is 0. So this is the equation that we've set up to solve the initial value problem. And we can do this, so then we distribute these constants with these vectors. Or you can set up an augmented matrix and find C1 and C2 that way. For this one, I'm not going to use an augmented matrix because there's some zeros here, so I don't think it'll be necessary. We can just say that C2 is equal to 1, and 3c of 1 is equal to 9. and then simplify this down so we find out that c sub 1 is just equal to 3. And so now we've solved the initial value problem, so the particular solution for this problem is going to end up being equal to x of t is equal to 3e to the negative t times this thing. Let's put an arrow there. um, Plus 1 times e to the negative t of that thing. So now we have our particular solution. And so now we can pick an answer from here. But the things are just distributed a little bit differently. So it's just a matter of figuring out how they did that. So I'm going to rewrite my particular solution in a way that looks like our answer choices. So when we do that, we end up with x of t is equal to e to the negative t times, so we have a 3 here and a 3 there, so we end up with negative 3 sine of 3t times, and then 9 cosine of 3t, and then another here, so we end up with plus cosine of 3t plus 3 sine of 3t. So let's see if we can get an answer from this. So yeah, this will end up being our final answer. I believe, is there an answer that looks like this? So we have cosine of 3t, 9 plus 3. Yes, okay, so I believe, yeah, so the answer to this question should be B. Let me just double check to make sure. So we have a cosine there, negative 3. Okay, that matches up with that, 3 sine. Okay, yeah, so the answer to this question is going to be B. Number 7. Given that x sub 1 of t equals this vector is a solution of the system of differential equations here, find another solution x sub 2 of t of the system such that x sub 1 of t and x sub 2 of t are linearly independent. So right off the bat, I know that we're dealing with a case of defective eigenvalues or repeated eigenvalues, whatever you want to call them. And the reason why is because of the fact that it wants us to come up with two solutions that are linearly independent. The fact that they're putting emphasis on that means that we're dealing with a case of defective eigenvalues. Because in a case of eigenvalues that aren't repeated, the solutions that you come up with are gonna be linearly independent by default. But in this case, they're not. We're gonna have to do a couple of additional steps to ensure linear independence while still having a valid general solution. And the cool thing is, it's only asking for the second solution. It's not asking for a complete general solution. And also the eigenvalue, one of the eigenvalues and eigenvectors is already given to us right here. If you're not sure, you can dissect it a little bit, where we know that since it's e to the 4t times negative e to the 4t, we can split this up a little bit, and this becomes e to the 4t times 1 and negative 1. And this 4, that's the eigenvalue, where lambda equals 4. And since we're dealing with a case of defective eigenvalues or repeated eigenvalues, it's going to be 4 with a multiplicity of 2. So the two eigenvalues we have is just 4 and 4. And so, yeah, so now we can completely just worry about the second solution. And so to do that, to find the second solution, the initial process is similar to just finding a normal eigenvector from an eigenvalue, where you plug in your eigenvalue into the equation of a minus lambda I multiplied by x sub 1 and x sub 2, and have it equal to 0 and 0. But in this case, instead of having it being equal to 0 and 0, we're going to set this equal to the first eigenvector we had, which is 1 and negative 1, like this. And then A is just this matrix, and then lambda I is just the identity matrix of negative lambda, like this. So when we plug everything in, we end up with an equation that looks like this, where when lambda is equal to 4, 3 minus 4 is negative 1. So negative 1, negative 1, 1, and 1 times x sub 1 and x sub 2, and set that equal to 1 and negative 1. And you can pick either the top row or the bottom row for this. I'm going to pick the bottom row because I just like not having negative numbers. So you'd have x sub 1 plus x sub 2 is equal to negative 1. And so similar to just finding a normal eigenvector, you have to pick two numbers for this case that satisfy this equation that aren't 0 and 0. But that doesn't mean that you can't use 0 as one of your numbers. And so in this case, I'm actually going to use 0 for one of my numbers just to make things easier for me. So I'm going to set x sub 2 equal to 0. And so when x sub 2 is equal to 0, x sub 1 just becomes negative 1 by default. So the new vector that we come up with is going to be equal to negative 1 and 0. And so from here, we can start writing out the solutions. So if we were to write a general solution, we'd have two terms since we're dealing with a 2 by 2 matrix here. So we'd say that x sub t is equal to our first solution, which is x sub 1t, which was already given to us conveniently here. So that would be c sub 1 times e to the 4t times 1 and negative 1. And then we add our second term. So I'm going to denote this as x sub 1 of t, and then plus, and then the first part of x sub 2t is going to be the same as x sub 1t. So we'd have a second constant c sub 2 times e to the 4t. And then this is where things are going to start to get a little different. Oh, also let me move this vector here. So I have a little more space. From here, this is where things are going to start to get different. So what we're going to do is we're going to multiply the first eigenvector we had, which is this. We're going to multiply that by t and add it to this vector that we have here. So we're going to have two parts here. So we're going to have a t times 1 and negative 1 plus our new vector here. So negative 1 and 0, like this. So we'd have a compound term like this. And so at this point now we have a linearly independent solution for x sub 2 of t here. And now let's say this was a system of 3 differential equations with 3 terms, and you ended up with an eigenvalue with a multiplicity of 3. Then you'd end up with 3 terms for the general solution, and you'd have to, and there's more things that you'd have to do. So the thing you have to look at it like is, instead of looking at it as just multiplying this vector by t, you have to look at it actually as we multiplied it by t over 1 factorial, like that. Yeah, and so, and the reason why is because if we let's say we had a third term, so we had like an x sub 3 t term down here, then it would still be the same case where the beginning is a c sub 3 e to the 4t, but what we'd have to do is we'd have to multiply the first vector by t squared over 2 factorial, and then this term by t over 1 factorial, and then add a new eigenvector to the end of that. And then if you had a fourth term, then you'd multiply the first vector by t cubed over 3 factorial, and the second one by t squared over 2 factorial, and then the third term by t over 1 factorial, and so on and so forth. But thankfully, we don't have to do that. And then also, I don't think this class deals with defective eigenvalues beyond 2 differential equations. So we can just simplify this down. So x sub 2 of t would end up just being equal to e to the 4t, and I'm gonna not put the constant in here because we don't have to worry about those constants for this question. And when we simplify everything out, we end up with, I'm gonna write this in red so that you can see that it comes from this first eigenvector here. So we have t and then negative t, because t times negative 1 is 1, and then minus 1 plus 0, and then it says 0, so we can get rid of that. So this ends up being x sub 2 of t, and we can pick an answer from here. And right off the bat, none of the answers look like what we have here, but I know that E ends up being equivalent. If you look at this t minus 2 term and this 1 minus t, it ends up being equivalent to what we have here. And so, yeah, so the answer to this question is going to be E. All right, number 8, the homogeneous differential equation of y double prime minus 3 over x y prime plus 4 over x squared y equals 0 when x is greater than 0 has two solutions of y sub 1 of x equals x squared and y sub 2 of x is equal to x squared ln of x. Use the method of variation of parameters to find a particular solution of the non-homogeneous differential equation of y double prime minus 3 over x y prime plus 4 over x squared y equals 2 where x is greater than 0. So the inhomogeneous differential equation that they give us is clearly identical to the homogeneous version of it, with the only difference being that it's equal to 2, where this is the this is the part that makes it inhomogeneous. And so when we're finding the general solution of a inhomogeneous linear differential equation, then the general solution is going to look something like this, where you have x sub c of t plus x sub p of t, where x sub c, that is the complementary solution, and x sub p is the particular solution. And to find the complementary solution of an inhomogeneous linear differential equation, it's the same process as a homogeneous one, where you set up a characteristic equation and go from there. And then for the particular solution, there are two main ways you can do that, whether it's by using the method of undetermined coefficients or by using the method of variation of parameters. And there are instances where sometimes the method of undetermined coefficients isn't really applicable, like it's not really effective, and that's when the method of variation of parameters comes in. It's a little bit more rigorous computationally, but in a problem like this, with the given inhomogeneous differential equation, it will actually make more sense to use the method of variation of parameters. So I'm going to do just that. And so we know that to find the particular solution of a inhomogeneous differential equation using the method of variation of parameters, we can use this formula, where we know that x sub p of t is equal to negative y, let me rewrite that, negative y sub 1 of x times the integral of y sub 2 of x times the inhomogeneous part here. So I'm going to call this f times f over the determinant of the Wronskian matrix plus y sub 2 of x times the integral of y sub 1 of x times f over the determinant of w with respect to x. And so recall that w, that's the Wronskian matrix, which is a square matrix involving, in this case, it's going to involve the two solutions given to us, where the two solutions and its derivatives, and that's going to give us a square matrix. And since we're dealing with two solutions and we need a square matrix, it's going to be a 2 by 2 matrix, where w, where w is going to be equal to y sub 1 of x and y sub 2 of x, and then y sub 1 prime of x and y sub 2 prime of x. And so that's, in this case, that's going to be equal to x squared and x squared ln of x, and then take the derivatives of those. So we end up with 2x and 2x ln of x plus x squared times 1 over x, which just simplifies down to x. So yeah, so this is our completed Wronskian matrix. And now we have to find the determinant of that. So the determinant of the Wronskian, since it's a 2 by 2 matrix, it's going to be the top left multiplied with the bottom right, subtracted with the bottom left times the top right. So that ends up being equal to x squared times 2x ln of x plus x minus 2x times x squared ln of x, like so. And then this evaluates to this, I believe this simplifies down to just x cubed. Yeah, wait, let me check. Yeah, this should simplify down. So we end up with x to 2x cubed ln of x plus x cubed minus 2x cubed times ln of x. Yeah, so these two terms cancel. So the determinant of the Wronskian here is going to be equal to x cubed. So now we have all of the terms that we need. We know that f is going to be equal to 2, and we have our two solutions, y sub 1 and y sub 2. So now we can just plug everything into the formula. So we can say that x sub p of t is going to be equal to negative x squared, because we know that we know that y sub 1 is going to be x squared, and we know that y sub 2 is going to be x squared times the natural log of x. So negative x squared times the indefinite integral of 2 times y sub 2 of x. So x squared ln of x over x cubed dx. Yeah, there we go. And then the second integral, we're going to end up with a second term of x squared ln of x times the integral of x squared, or 2x squared, over x cubed dx. So I'm going to evaluate the first integral first, and neither of these integrals are that bad. We can see that this second integral is pretty straightforward, and then this first integral, once we cancel everything out, it's just going to be a u substitution. So I'm going to simplify this a little bit. So these x's cancel, so this integral ends up being equal to 2 times ln of x over x dx. And yes, this can be solved with a u substitution, where we're going to set our u equal to ln of x, and doing this is going to allow us to cancel it out with this x. So du is going to be equal to 1 over x dx. So dx ends up being equal to x du. Yeah. And so yeah, so now we can plug everything back in. So this integral ends up being 2 times u times x du over x, and then these x's cancel. So this becomes the integral of 2u du, which just equals u squared. And so yeah, so we've evaluated this first integral. So now we can focus on the second integral, which is also super simple. This just simplifies down to the integral of 2 over x dx. And then that just equals 2 times ln of the absolute value of x. So yeah, so now we can plug everything back into, now we can plug it back into the formula. So we can say that x sub p of t is equal, oh, and then also one more thing that we have to do, yeah, we also have to have this u be back in terms of x. So u squared, that becomes ln of x squared. Yeah, there we go. Now we're done. And so now we can plug everything back in. So x sub p of t is going to be equal to x squared times ln of x squared plus x squared ln of x times 2 ln of absolute value of x. Even though it's an absolute value, it can still be multiplied with this ln of x here. So when we simplify this down, we just end up with negative x squared times ln of x squared plus 2x squared ln of x squared. And so this ultimately reduces down to a particular solution of just x squared ln of x squared. So yeah, this ends up being the final particular solution of this inhomogeneous linear differential equation. So yeah, this is the final solution to this question. All right, number 9. Consider the linear system x prime is equal to a of x, where a is equal to this matrix, and find two linearly independent solutions of the system, and use the solutions found in part A to calculate the exponential matrix e to the at. So the process of finding the linearly independent solutions, that's just normal eigenvalue method stuff for systems of linear differential equations. So I'll set up a determinant where we say that the determinant of a minus lambda I is going to be equal to 0, and then we're going to solve for lambda, where a is this matrix, and negative lambda I is the identity matrix of negative lambda, which looks like that. So when we put everything in, we'll end up with a determinant that looks like this. So negative 5 minus lambda, 1, 4, and negative 2 minus lambda, and set that equal to 0. And then to find the determinant of a 2 by 2 matrix, it's just top left times bottom right minus bottom left times top right. So that ends up looking like negative 5 minus lambda times negative 2 minus lambda minus 4 equals 0. And this simplifies down to lambda squared plus 7 lambda plus 6 is equal to 0. And then to find lambda from here, I think the best way to do that in this case would be to factor. If you're feeling really paranoid, you can use the quadratic formula or something like that, but I'm going to factor this. And this factors out to lambda plus 1 times lambda plus 6. And so from here, and then set that equal to 0, and then we can find that lambda is equal to negative 1 and negative 6. And so so now that we have our two eigenvalues, we can come up with the corresponding eigenvectors from there, and then we'll have our two linearly independent solutions. And since these are two real eigenvectors that aren't repeating or defective or whatever, or not complex, we don't have, finding those solutions is going to be pretty simple, and we don't really have to take any extra steps. So I'm going to start by finding the first eigenvector, so plugging in negative 1 for lambda. So when lambda is equal to negative 1, the matrix we end up with is negative 4, 1, 4, and negative 1 times x sub 1 and x sub 2 equal to 0, 0. And that's going to, I'm going to use the bottom row to make an equation. So we can say that 4 x sub 1 is equal to x sub 2. And so our corresponding eigenvector, keeping things simple, I'm just going to use 1 and 4, since they're just opposites of each other. So we have our first eigenvector. And then for the second eigenvalue of negative 6, when lambda is equal to negative 6, then the matrix we end up with is going to be 1, 1, 4, and 4. Yeah. Times x sub 1, x sub 2 equals 0 and 0. And so for this second eigenvector, I'm going to use the top row because it's just 1, so we end up with x sub 1 is equal to negative x sub 2. So our corresponding eigenvector is just going to be 1 and negative 1. And yeah, just to keep things simple. So we have our two eigenvectors and we have our two eigenvalues, so we can come up with two linearly independent solutions. So for the first one, I'll say that x sub 1 of t is equal to e to the negative t times the eigenvector of 1 and 4, and then x sub 2 of t is going to be equal to e to the negative 6t times 1 and negative 1. So yeah, so we have completed the first part of this question. So this is going to be equal to part A. Yeah, this is the answer for part A. And now we can move on to part B. All right, and so from here, now we can focus on the second part of this question, which says to use solutions found in part A to calculate the exponential matrix e to the at, which I have circled in purple here. So for the second part, I'm going to be using a different color to avoid confusion. And to find the matrix exponential here, there's a formula that you can use for that, and that's kind of what this question is pointing towards. So we can say that the formula for that, for finding the matrix exponential from these solutions, is we know that e to the a of t is equal to the fundamental matrix, which I'm going to denote as phi. So phi of t times the inverse of the fundamental matrix, phi inverse evaluated at 0. And what the fundamental matrix is that is just simply distributing these e terms from our solutions into its corresponding eigenvector and then squishing them into one matrix. And so when we do that, our fundamental matrix is going to be equal to phi of t is equal to e to the negative t, 4e to the negative t, e to the negative 6t, and negative e to the negative 6t. And then to find the inverse of this, the cool thing is we're dealing with a 2x2 matrix. So finding the inverse of a 2x2 matrix, there's also a formula for that. You don't have to worry about doing any row reductions and matrix multiplication like you do with larger matrices. And we can also assume that this matrix is invertible. We don't have to worry about the bajillion different conditions from the invertible matrix theorem, if you remember that. To find the inverse of a 2x2 matrix, let's just come up with an example here. Let's say that G is equal to A, B, C, and D. So in this case, the inverse of G is going to be equal to 1 over the determinant of G. So AD minus CB multiplied with its adjugate matrix. And what that is we're going to flip the position of A and D. So D ends up here and A ends up here. And then we're going to flip the signs of C and B. So negative C and negative B. And then you plug in all your numbers and simplify this down and you'll have an inverse. So I'm going to apply that to our fundamental matrix. So the inverse of phi at t is going to be equal to the determinant of that, which is 1 over e to the negative t times negative e to the negative 6t minus 4e to the negative t times e to the negative 6t times its adjugate matrix, which I'll add on later. And this simplifies down to 1 over 5 times e to the negative 7t. And now I'm going to bring the adjugate matrix in. So we're going to swap the top left term with the bottom right term. So we have e to the negative 6t here and e to the negative t here. And then flip the signs of the bottom left and the top right. So negative 4e to the negative t and negative e to the negative 6t. And so now we have our inverse. And then we can also just distribute this fraction in. And when we do that, the invertible matrix, the inverse of our fundamental matrix is going to be equal to e to the t divided by 5, and then e to the t divided by 5 again, and then negative 4 over 5 times e to the t, and e to the 6t over 5. And now we can evaluate this at 0. So the inverse of our fundamental matrix evaluated at 0, we're just plugging in 0 for t. That gives us 1 over 5, 1 over 5, negative 4 over 5, and 1 over 5. And now we can multiply this with our original fundamental matrix, which we have over here. So when you do that, let me set up everything. So ultimately, e to the at is going to be equal to e to the negative t, e to the negative 6t, 4e to the negative t, negative e to the negative 6t, times 1/5, 1/5, negative 4/5, and 1 over 5. And so now we're going to have to do a little bit of matrix multiplication. So what this ends up looking like is this is going to give us another 2x2 matrix because we're multiplying a 2x2 matrix with a 2x2 matrix. And so in order to do that, we need to do this. So the new matrix is going to be, and I'm going to use a bunch of different colors here for that. So for the top left term, let's use red. That's going to be the top left term is going to be this row multiplied with this column. Yeah. So when we do that, so for the top left term, we're going to end up with actually, you know what? I think actually no, we can just use one color for this. So we end up with e to the negative t over 5 minus 4/5 e to the negative 6t for our top left term. And then for the top right term, we need to multiply this row, or take the dot product of this row with this column. So what that ends up looking like is e to the negative t over 5 again, minus, or plus, plus e to the negative 6t over 5. And then for the bottom left, we're going to multiply, or we're going to take the dot product of this row with this column. And so to do that, you end up with, let's see here, you end up with, negative 16 e to the negative t over 5. Wait, no, that's wrong. That's wrong. You end up with, my bad, you end up with 4/5 e to the negative t plus 4/5 e to the negative 6t. And then for the bottom right, you take the dot product of the bottom row of this matrix with this column. And so what that ends up being is 4/5 e to the negative t minus e to the negative 6t over 5. And if I didn't make any algebra errors, this should be the final matrix exponential. We can also simplify this a little bit, so I can also do that. But yeah, this should be this giant ugly matrix is going to be equal to our matrix exponential. So when we simplify that, let me put the simplified answer over here. We end up with e to the at is going to be equal to e to the negative t plus 4e to the negative 6t over 5, and then e to the negative t minus e to the negative 6t over 5 again. And then we end up with 4e to the negative t minus 4e to the negative 6t over 5 again. And then once again down here, we end up with 4e to the negative t plus e to the negative 6t over 5. And once again, if I didn't make any algebra mistakes, this should be the final matrix exponential. So this would be the answer to part B. Yeah. I think I got everything. Okay, yeah, cool. So yeah, this is going to be the complete problem for number 9. Like that. Yeah, here we go. Nice. Number 10. Consider the first order system x prime equals y, y prime equals 3x, and x of 0 equals 4, and y of 0 equals 2 root 3. Find the solution and show that its trajectory is a branch of a hyperbola. So from here, unfortunately, we also have to set up the system ourselves and put it into matrix form ourselves, but the values they give us aren't that bad. It's going to be pretty simple. So we can just say that since wrong color, so x prime, since we know that's equal to y, we can put this in the top part of our matrix, and then since y prime is equal to 3x, we can set up our matrix like this. So we have that x prime y prime is going to be equal to I'm going to put x, I'm going to put the x terms in this column and the y terms in this column. And so our matrix, the matrix form, our, our something prime equals ax thing is going to end up looking like 0, 1, 3, and 0, like this, times x and y. And so from here, we can find the solution by using the eigenvalue method as usual. So taking the determinant again of determinant of A minus lambda I. A is this matrix, lambda I is the identity matrix of lambda. So that ends up looking like a negative lambda, 1, 3, and negative lambda. And set that equal to 0, like this. And so when you simplify everything out, you end up with lambda squared minus 3 is equal to 0. And so our eigenvalues, we end up with lambda is going to be equal to plus or minus the square root of 3. And so that's cool. We have two real eigenvalues. One is positive and one is negative. So the phasing behavior of this system is we're going to end up with a saddle point. That's going to be important for later. And so with that, we can find the corresponding eigenvectors. So I'm going to start with the positive root first. So when lambda is equal to positive root 3, then the matrix we end up with is negative root 3, 1, 3, negative root 3, times x, y is equal to 0 and 0. And I'm going to use the top, actually no, I am going to use the top row to find our eigenvectors for this. Actually, you know what? Actually, it doesn't really matter. We can use either one here. I was just trying to think of like which one would be nicer for later down the line, but I don't think it really matters. So we say that the negative root 3x plus y is equal to 0. And so our corresponding eigenvector is going to be equal to 1 and root 3 when we move things around. And this will satisfy this equation, so this is a valid eigenvector. And then since roots come in conjugate pairs, we don't even have to do all this computation to find the second eigenvector. We can just come up with a conjugate eigenvector where this bottom term is flipped, so we have a second eigenvector that's just equal to 1 and negative root 3, like this. So we have our two eigenvectors from here, which is nice. So then we can come up with a general solution, which we can say that x and y in vector form is going to be equal to some constant e to the root 3t times 1 and root 3 plus c2 e to the negative root 3t 1 and negative root 3, like this. And so yeah, now we have our general solution. And we can now solve the initial value problem, which the parameters for that are given here. We're evaluated when x and y is equal to 0, x is equal to 4, and y is equal to 2 root 3. So when we plug those things back in, we can say that 4 and 2 root 3 is going to be equal to c1 times 1 over root 3 plus c2 times 1 over, no, not 1 over, just 1 and negative root 3. This is a vector, not a fraction, my bad. And so to find these, you can either set up a couple of equations and substitute things in here and there, or set up an augmented matrix and row reduce it to find C1 and C2. So I think for this one, I'm going to set up an augmented matrix and row reduce that. So our augmented matrix is going to end up looking like 1, 1, 4 with a bar here, and then root 3, negative root 3, and 2 root 3. And then doing the row reductions here, we have 1, 1, 4, 0, because this is a negative root 3, so this becomes negative 2 root 3, and then 4, negative 4 times negative root 3. This also becomes negative 2 root 3. And then from here, the next thing we end up with is 1, 0, 1, 1. This goes here. And then 1, what is it? Since we canceled that out, we end up with a 3 here, I believe. Yeah, this should be correct. Yeah, okay, cool. So, yeah, as a result, we can say that C2 is going to be equal to 1, and C1 is going to be equal to 3. And so we've solved the initial value problem, so the particular solution for this IVP is going to be equal to xy is equal to 3e root 3t 1 root 3 plus e negative root 3t 1 negative root 3. And so now we have all the information we need to show that the trajectory of this solution is going to be the branch of a hyperbola. And what I mentioned earlier is since we have a positive and a negative real eigenvalue, that's going to give us a saddle point at the origin, which is going to help us to kind of visualize it. So I'm going to make a graph here. So if we have our graph like this, let me zoom in a little bit, and then also increase the thickness now. For that, we'd have like our x and our y plane. And the first thing I'm going to do is I'm going to graph the trajectories of our eigenvectors. And so for our first eigenvector, we have 1 root 3. And so the trajectory of that eigenvector is going to look a little something like this, where you have a line that goes diagonally like that. And since the x term and the y term are positive, this eigenvector is going to be radiating outwards like this, if that makes sense. And then we have a negative eigenvector here. Well, we have a negative y term, and the eigenvector through the origin for that, when we visualize that, is going to look like this, where we have actually I'll use red. So the corresponding, oops, let me get rid of that. The corresponding eigenvector is going to, for that second eigenvector, is going to look like this, where we have a line that looks like this. And since the y term is negative, this is going to be radiating inwards, so the trajectory of things is going to look like this, if that makes sense. And so then when we start graphing like the phases at any given time, the branches of that, if we let's say we start from, and now let me use a different color again. If we started from here, what's going to happen is the arrows are going to go down like this until it hits the origin, and then once it hits the origin, it's going to start to curve upwards again and look like this. And then if we were to start from like here or something, then it would do the same thing, where it gets closer and closer to the origin until it gets to the origin, then curves again and goes down like this. And so as you can see, these trajectories are starting to look like a hyperbola, because if you recall, usually hyperbolas, I'm going to have another graph here. Hyperbolas usually look like this. Like if we had like our two asymptote lines here like this, then the corresponding hyperbola would look like something like this, where you'd have like that, if that makes sense. And so as a result, you can see that the trajectory of the points here behaves a lot like my example over here. And so from here, we can show that the trajectory of the solution is going to be the branch of a hyperbola. And then also we found the general solution. We also completed the initial value problem. So this completes the last question for this exam. Nice.